Okay, so the idea of torque is basically the rotational version of force, and it's what you have to do to an object to make it rotate. For example, let's say you just got some object. Let's say you just got this object floating in space, and you want it to rotate. What would you have to do to it to make it rotate? Or if it's already rotating, to change its rotation, what would you have to do to it?
Change the angle?
What was that?
Like change the angle?
That's what the rotation is. Rotation is the process of making of the angle changing. And so you can compare this in a lot of ways to translational motion. Translational motion means the position is changing. Versus rotational motion means the angle is changing. The angle of orientation. Like if an object is rotating, then the angle it makes with, let's say, the vertical or something is in the process of changing. And we describe the rate at which it's changing using this idea we call velocity. Translational velocity we define as the derivative of position, how fast the position is changing. The rotational version of that would be rotational velocity, which is just how fast the angle is changing. Usually written as the Greek letter omega, lowercase omega, is just the derivative of angle. So translational velocity, V, is how fast the position is changing as time passes. Rotational velocity, omega, is how fast the angle is changing as time passes. Usually measured in radians per second or sometimes degrees per second. But radians usually work better with all the formulas. Any questions on that so far? So if an object is just translationally moving, let's say it's just drifting through space, do you need to do anything to keep it moving?
You have to have like a constant force on it?
Is a constant force necessary just to have it keep moving at the same speed?
No, without friction, I don't think so. I think it'll just stay in motion.
Right. If there's no force at all, no friction, no push, nothing, then it's just going to keep moving at the same speed in the same direction forever. If there is a force, what's that force going to do to it?
Change the speed.
Right. The force causes a change to that motion, a change to the velocity. So force causes a change to the velocity. For rotation, we have a very similar idea. If an object is rotating and there's nothing acting on it at all, it's just going to keep rotating at the same rate forever. If you want to change the rate at which it's rotating, either make it spin faster or make it spin slower, or change the axis it's spinning around. Like let's say you've got something spinning around this axis, and you want to change it so it's now spinning around this axis. Changing the axis it's rotating around counts as a change in velocity or change in rotational velocity. Rotational velocity, in fact, angle itself actually counts as a vector. You can associate a direction with a rotation, and the direction we use is the axis that the object rotates around. For example, if you have an object, let's say you've just got this spinner that's spinning like this. It's rotating around a vertical axis, this up and down axis that the object is rotating around. So if this is spinning, we could treat that as a velocity vector, a rotational velocity vector, either straight up or straight down. And the way we decide straight up versus straight down is using what's called the right-hand rule. If it's spinning like this, you curl the fingers of your right hand in the direction it's rotating, and your thumb tells you the direction of the angular velocity, rotational velocity. So this rotation would be treated as an upwards rotation. Nothing's moving upwards. Upwards is just the axis that everything's rotating around. Likewise, if we spin it the other direction, rotating this way, curl your fingers of your right hand in that direction, we would call that a downwards rotation. Again, nothing's moving downwards. Downwards is just the axis that it's all rotating around. So we usually call that the right-hand rule for rotations. It's just a way of assigning a direction to a rotational motion. Similarly, if it was spinning like this, curl your fingers in the direction of spin, we would treat that as, I guess that would be towards you. Or if it was spinning like this, that would be away from you. Or spinning like this, that would be to, I guess that's to your right. And then this would be to your left, or whichever direction that is. Any other questions on that so far? The direction of rotation. To make it rotate though, what have I been doing to this to make it start rotating in the first place? Or to change its rotation once it's already rotating?
You like pushed it, right?
Yeah, I pushed it. I was applying a force. But not just any force will work. For instance, if I just push on it like this, I'm not really causing much rotation. Because this force, I'm applying a force towards what point on the object? If I just...
Well, you're not pushing it in the direction of its motion.
It's not about the, I mean, it's not moving at all yet. I'm pushing it, yeah, if I'm pushing it directly towards the center, a push directly towards the center of rotation, directly towards the axle or the hinge doesn't really do anything. If I want this push to cause rotation, I need a push that's off center. That causes rotation, an off center push. And that's really what a torque is. A torque is just a push, a force that's off center. So torque is an off center force in terms of where the force is. Previously, we haven't really been caring where the force is, just how much force and in which direction. But if we're talking about torque, it matters where the force is being applied on the object. A torque is an off-center force that can cause rotational change. I'm not going to say that can cause rotation because maybe the object's already rotating. The torque causes the rotational velocity to change. It causes a change in how fast it's rotating or which axis it's rotating around. For example, if I've got this object that's not already rotating and I apply a torque, I can make it start rotating. Not rotating, changes to rotating. Or maybe it's already rotating and I apply a torque to make it rotate faster. Or maybe apply a torque in the other direction to make it slow down. Or if it's already spinning really fast, I can apply a torque to make it change the axis it's rotating around. Those all count as changes to the rotational velocity, so they all require torque to make it happen. Any other questions on that so far? So let's take a look at how we would calculate how much torque. The general idea is that in much the same way that force causes a change to the translational velocity, torque, usually written as a Greek letter tau, causes a change to the rotational velocity, omega. And this has a huge application to statics problems. If you want something to stay still, if you want no change to the velocity, the translational velocity, it's not moving and you would like it to keep not moving, you need to make sure the forces all add up to 0. If you also want no change to the rotational velocity, if it's currently not rotating and you want it to continue not rotating, you need to make sure the torques all add up to 0. So in any statics problem, any situation where you want something to continue not moving at all, you need to make absolutely sure the forces all add up to 0 and separately the torques all add up to 0. So let's take a look at how we would actually calculate torque. Let's say, for example, that you have some object. Let's say you've got let's say a door. Let's say we're looking at this top-down view of a door attached to a wall. And let's say this is a top-down view. So we've got, let's just call these directions north, south, west, east for convenience. So this doesn't actually mean up, this means going to the north. Up would be presumably this way, and down would be this way. So let's say you wanted to rotate this door. First of all, if this does rotate, what point would it be rotating around? What would we be treating as the center of rotation here?
The wall?
Yeah, the point where it's attached to the wall. We presumably have a hinge here. We're going to call that hinge the pivot point. The pivot point, sometimes called the hinge or the axle or the center of rotation, is just the point that it rotates around. That if this object rotates, it's going to be rotating around that point. So the pivot point is the one point that stays in place while the object is rotating. So let's say you want to open this door. You want to make this door start rotating. You want to apply a force. And where should you apply that force to get the most results, the largest rotational results?
Is the force supposed to be the same, like assuming that it's the same?
Yeah, let's say there's a certain amount of force you're allowed to apply. You can apply, let's say, 50 newtons of force to this door, but you can apply that force anywhere you want. Where should you apply that force?
On the farthest part of the door, like farthest away from the pivot point?
You can apply 50 newtons of force. If you apply the force to the hinge, nothing happens. Pushing on the hinge of a door doesn't really accomplish anything. If you're pushing close to the hinge, you get very little result. But if you push far from the hinge, you get the most result. So let's say you put your 50 Newton force here. That's some distance away from the pivot point, and we call that distance the radius or radial vector. So that would be r. Radius in the sense that it's distance outwards from some center point. That's called the radius vector, or sometimes the moment arm or lever arm. Or just the radial distance, radius. So that's the distance from the center to the location where the force is being applied, expressed as a distance vector or displacement vector. And then, of course, doesn't have to be the full length of the lever or door or whatever. It's just the distance from the center, from the pivot point, to whatever location you're applying a force at. And you get the largest amount of torque if radius is as large as possible. In fact, they're going to be proportional. The torque, the magnitude of torque, because torque counts as a vector. Magnitude of torque is going to be proportional to the radial distance. The longer the radius is, the more torque you get. And of course, it's also proportional to the amount of force. If you applied twice as much force in the exact same scenario, you get twice as much torque. So magnitude of torque is also directly proportional to the amount of force. But those aren't the only things that matter. If you apply 50 newtons of force at a distance, let's say this is 2 meters, for example, a very large door. If you're applying a 50 Newton force at a 2 meter distance, what's the one other thing that you could modify?
The angle?
Yeah, you could change the angle. This presumably would not be the usual way you open a door. You don't usually push in this diagonal direction. You could, but it would be more effective to push in which direction?
Perpendicular to the door?
Yeah, you get the most result, the most torque, if you take that same force, but you apply that force perpendicular to the radius itself. So you get the most torque if the angle here, the angle between radius and force, is perpendicular. You get the most torque when the angle, usually called theta, is 90 degrees. What angle would lead to the least torque, no torque at all?
180.
Yeah, if it's 180, like if you're pushing, so if you make the angle 180, so you got radius vector, swivel the force vector all the way around. If you're pushing towards the pivot point, like if you just grab the end of the door and start pushing straight towards the hinge, you're not really doing anything rotationally. So a 180 degree angle would lead to no torque at all. and also a 0 degree angle if the radius and force are in the same direction. This would technically be 0 degrees because the radius and force have no difference in the direction, 0 degrees worth of difference. That also creates no torque. If you just grab the end of the door and pull straight away from the hinge, you're not causing any rotational change at all. So you get no torque when the angle is 0 degrees or 180 degrees. And this suggests we're going to need a certain trigonometric function. What trigonometric function has its largest value when the angle is 90 and becomes 0 when the angle is 0 or 180?
Sine.
Yeah, sine of the angle is going to be perfect here. So we also say that torque is proportional to sine of the angle between radius and force. And it turns out those are the only things that influence it. You can modify the amount of torque, the rotational push, by changing the amount of force, by changing how far the force is from the radius, and by modifying the angle of the force relative to the radius. So we can just multiply those together to get a definition for torque. The magnitude of torque anyway, because it is a vector quantity, we're going to need to consider direction as well. The magnitude of torque is just radius times force times sine of the angle between them. Any questions on that so far?
Would force need a vector on it too, or it doesn't matter here?
Force is a vector, but we're treating it as we're looking at just the magnitude of force here. So this is magnitude of radius times magnitude of force. Strictly speaking, these should be in magnitude, the double absolute value bars also. Mm-hmm. But often if we write a vector without the vector sign over it, like if we just write F without the vector sign, that usually just means magnitude of that vector.
Okay.
So F with the vector sign is a vector. If we write double absolute value bars of F with a vector sign, that's its magnitude. And usually, this is a little less formal, but if you write the variable without the vector sign, that also usually implies we're talking about magnitude as well. So if you see what would usually be the name of a vector in a formula, but without a vector sign, that generally means the magnitude. So we could also say, for instance, just tau without the vector sign equals r times f times sine theta. But I'm writing this as a vector in absolute value bars to emphasize this is a vector quantity. We're just looking at only its magnitude at the moment. Any other questions on that so far? So let's take a look at some of the implications of this. This is essentially the definition of magnitude of torque here. But in order to figure out how much that actually is, let's look at some special cases. We were looking at so far at if it's perpendicular or if the force is directly towards the pivot point or directly away from the pivot point. So if we examine those with this formula, if the force vector is perpendicular to the radius vector, if the force is exactly perpendicular to the moment arm, then we've got theta being 90 degrees. What's sine of 90 degrees?
1.
So we just get r times f times 1. So if we're talking about the force being perpendicular to the radius, then the torque, the magnitude of torque is just radius times force, and that's it. And of course, you could get that using this formula in its entirety. It's just that when you plug in 90 degrees for theta, sine of 90 degrees becomes 1, so we just get r times f. Alternatively, if the force is parallel to if the force vector is parallel to the radius vector, if theta equals 0 degrees or 180 degrees, that is, in other words, F is directly towards or away from the pivot point. Then you plug in 0 degrees for theta or 180 degrees for theta. What's sine of 0 or sine of 180?
0.
So you get R times F times 0, which means no torque at all. So these are the two extremes. If you have force being exactly perpendicular to radius, then the torque is just radius times force, and that's it. If the force is exactly parallel to the radius, if you're pushing straight towards the pivot point or pulling straight away from the pivot point, then you get no torque at all. And there are a couple other situations where you get no torque. You get no torque if sine theta becomes 0, or since this is a product, if any one of these three things is 0, then the whole thing becomes 0. No force, of course, means no torque. No force means no torque. If you're not pushing on the door, of course, you're not causing any rotational change. But also, 0 radius means no torque. No radius vector means no torque. And what would 0 radius mean?
Like right at the hinge.
Yeah, if you're applying the force exactly at the location of the pivot point, then the direction doesn't even matter. The amount of force doesn't matter either. If you're applying the force at the pivot point, R is 0, so you get 0 torque. That is, in other words, if the force is at the pivot point. So these are basically the three situations where a force would lead to no torque at all. And well, no force at all, of course, means no torque. But also if the force is exactly at the pivot point, or if the force is pointing directly towards the pivot point or directly away from the pivot point, in those circumstances, you would get no torque at all. In any other circumstances, if you have a force that's not at the pivot point and not pointing directly towards or away from the pivot point, then that force also counts as a torque. And I say also because I want to emphasize that it still counts as a force as well. If you're adding up all the forces, you need to include all the forces acting on the object, whether they create torques or not. Separately, you also want to add up all the torques acting on the object, all the forces that count as torques, calculate the torque, add all those up as vectors, and that'll tell you the total torque acting on the object, which is useful for figuring out, does this rotationally accelerate? If so, in which direction and how much? Or if not, then it would just continue rotating with whatever rotational velocity it already had, which might even be 0. Any other questions on that so far? And a couple of other things about the geometry of this. Because this is just one possible formula that we could write out here. This is the usual one I tend to think of when I think of torque. But a couple of other ways you could write that. Let's say you have a lever shaped like this. Make that bigger. And it's got its pivot point over here. And we're applying a force to it at, let's say, this location and pulling, let's say, horizontally. Then the radius vector is going to be from the pivot point to this location of interest, the location where the force is being applied. So that's our moment arm, or our radius vector. And then theta, if you imagine just continuing this radius vector out here, theta is going to be the angle between the line of the radius vector and the force itself. So that's theta. You could also interpret theta as this angle. They're different angles, but they end up having the same sign. Sine of both of those angles should be the same. So it doesn't really matter which angle you use here. So I usually just use whichever of those two angles is the acute angle, just to keep things simpler, but they'll have the same sign anyway. So we're calculating radius times force times sine of theta. And one interesting way to look at that, if you combine the force times sine theta, let's say torque equals radius times F sine theta. If you multiply the magnitude of a vector times sine or cosine of an angle, what does that remind you of? What are we usually trying to find if we're multiplying a magnitude times sine or cosine of an angle?
The hypotenuse?
Yeah, or the other way around, really. Usually we treat the magnitude of the vector as the hypotenuse. And by multiplying that hypotenuse by a sine or cosine of theta, what are we typically trying to find? This is usually how we split the vector up into what?
X and Y components?
Yeah, X and Y components, or some sort of components. In this case, it's not really going to be X and Y components. It's going to be, if we're saying theta is the angle between the radius vector and the force, if we're using sine of that angle, we're treating force as the hypotenuse. We're not splitting it up into the conventional X and Y components. Instead, we're splitting it up into a component in the direction of the radius, and then perpendicular to that, a component in the direction perpendicular to the radius. So if you imagine continuing the radius vector, that would be, if this is the force vector, what we've just done is we've drawn in these two new components, not the usual XY components, but instead a tilted axis. We're basically looking at an axis parallel to the radius and another axis perpendicular to the radius. So instead of splitting the force into the usual X and Y components, we split it into a parallel component, usually written as F and then a little parallel sign, and a perpendicular component, F and then a little perpendicular sign. So F parallel and F perpendicular are the components that we're splitting F into using this tilted axis system. Because it usually makes sense, if you're comparing two vectors, it generally makes the most sense to treat one of the vectors in terms of the other vector's directions. So we're splitting up the force vector into components using a coordinate system based on the radius vector. And these are sometimes often also called the parallel direction is also called the radial direction, in the sense that it's in the direction of the radius. And the perpendicular direction is also sometimes called the tangential direction. That's tangential in the sense of the tangent to a circle. Like if you were to take this door and actually rotate it, the tip of the door would be moving in a circular path. And of that circle, the radius vector is literally the radius of that circle. The motion of the object would be in a direction tangent to the circle itself. So the perpendicular direction is called the tangential direction because it's tangential to that circle of motion. Any questions on the geometry there so far? So in that triangle, if this is a right triangle and theta is this angle here, the angle between the continued radial direction and the force direction, what would F sine theta be calculating? Which component are we actually finding if we're calculating F sine theta? Sine is generally describing ratio of what side over what side.
Opposite over hypotenuse.
Right. And from this theta, opposite would be the perpendicular side. And hypotenuse would be the force itself. Multiply both sides by F. and f sine theta would be the perpendicular side. So this f sine theta could be replaced with just the perpendicular component. And then that's being multiplied by the radius to get torque. So this is an alternative formula we could use for torque. Instead of thinking of torque as radius, like the complete radius times the complete force times the sine of the angle between them, you could instead think of torque as the complete radius times not the entire force, but just the component of it in the perpendicular direction. Because the perpendicular component is what's actually causing rotation. If you think of this force as somebody pulling straight away from the pivot and somebody pushing perpendicular to the rotation, to the radius, the pull straight away from the pivot does nothing. That causes no rotational change at all. But the push perpendicular to the radius, that's where all the torque is coming from. So it's very useful to think of torque as the complete radius, distance from the pivot to the location of the force, multiplied by just the perpendicular component of the force, because that's really all that's doing the job here. Any questions on that so far? And I want to emphasize that's exactly the same result as r times f times sine theta, because f sine theta is f perpendicular. So this isn't really a different formula. This is just a different way of writing the same formula. R times f times sine theta, or the complete radius times just the perpendicular component of the force. Alternatively, instead of splitting the force into components, you could keep the force exactly as is and split the radius vector into components. So getting rid of the components of force, we're going to treat force as just this whole vector now. We're still going to treat theta as the angle between them. But now let's keep the force and instead split the radius into components. If we split up the radius into a component perpendicular to the vector and a component parallel to the vector, let's say we draw in a component parallel to the force vector and also a component perpendicular to the force vector, making a complete right triangle here. So we've taken our radius vector and much in the same way that we previously created a new coordinate system based on the radius direction, we're now creating a new coordinate system based on the force direction, making a parallel component parallel to the force and a perpendicular component. So in this sense, we're now keeping the force exactly as it is, but we're splitting up the radius into a parallel component and a perpendicular component. And we could translate the angle into this angle. Since these are just two lines crossing each other, these two angles would be considered vertical angles and they're congruent. So this is just another copy of theta. In that context, how would you relate theta to the other sides, specifically using sine? In this triangle, sine theta would be what over what?
R parallel over R.
Is the parallel component opposite or adjacent here?
Adjacent.
So if we were dealing with sine, we want the opposite side, so that would be perpendicular. If we were using cosine, we would definitely have R parallel over R. But sine should be opposite over hypotenuse, so that's going to be R perpendicular over R. And then if we do the same sort of procedure, if we just multiply both sides by R, we get R sine theta equals R perpendicular. And this gives us another way of writing torque. Previously, we tried combining the F times sine theta to get F perpendicular. But multiplication is commutative and associative. We can change the order of R, F, and sine theta however we want. If we write this as F times R times sine theta, and combine the r sine theta first, we just found that r sine theta is just the perpendicular component. Multiply that perpendicular component by the force, and this tells us the torque as well. So once again, only the perpendicular component matters. The parallel component doesn't really do anything, at least not in terms of torque. So this gives us a third way of writing torque. Torque can be written as the complete radius times the complete force times the sine of the angle between them, or the complete radius times only the perpendicular component of force, or the complete force times only the perpendicular component of radius. So three different ways of calculating torque, all leading to the same result. They're really just three different ways of looking at the same formula. But each one of these can be more or less useful in different circumstances. For instance, if you can easily measure the distance from pivot to the location, and you know how much force, and you have some way of measuring the angle between them, this is probably going to be the easiest to calculate. Or if you don't know the angle, but you need, or maybe you know the angle or not, but you need to split up the force into components anyway. Like let's say the radius is already in a direction that you want to split the force into components of anyway. Maybe let's say the radius is horizontal, and you're going to be splitting the force into x and y components anyway. Then this would probably be the most useful, because F perpendicular is part of the result you're looking for elsewhere as well. Or alternatively, F times R perpendicular is often most useful in certain practical applications. Somebody mentioned bridges earlier. If we take a look at a bridge, for example, let's say we have, let's say we've got a cliff here, we've got a ramp leading up to a platform. And let's say this is the main thing we're considering. We've got a car that's located here. And realistically, we probably want to consider the mass of the bridge as well. But let's say we're looking at the car as the only object we care about. What forces would be acting on the car? Or why do we have to hold the car up in the first place? The bridge has to hold the car up to counteract what other force?
Gravity.
Gravity, which is going to be presumably pulling straight down. So the gravity is pulling the car down, the bridge is holding the car up. That means the car's tires are pushing down on the bridge. So the bridge is experiencing this downwards force of the car. And maybe there's more of the bridge over here, but we only really care about the point up to, in fact, let's go ahead and draw out more of the bridge. Let's say this is also going towards some other cliff on the other side. In this context, if we want to figure out, if we want to analyze the forces acting on the bridge, what would you probably want to treat as the pivot point here? If this bridge started rotating, what point would it be rotating around? Like let's say something on the bridge breaks and the whole thing starts collapsing. If you treat that collapse as a rotation, what point would the remnants of the bridge be rotating around?
The middle?
The middle? Like these sides are going to start collapsing while the middle stays perfectly still?
Oh no, it would be like the opposite, right?
Yeah, typically we'd expect probably one of the edges here, like maybe this bridge, let's say this point breaks and the rest of the bridge starts collapsing like this. We would treat this corner, this point where it contacts the cliff, as the pivot point. Or alternatively, maybe this side breaks and it starts collapsing like this. So we probably want to treat one of these corners, one of these points where it contacts the ground, the firm ground there, as the pivot point. And you could really do either one. The fact of the matter is, if an object is rotating, you want to treat the point that it's rotating around as the pivot point. If it's not rotating, you can really treat any point as the pivot point. but it usually makes the most sense to choose the point that it could rotate around if it were to start rotating. So I would use one corner or the other, one edge or the other here, the cliff side as the pivot point. So if we use that as the pivot point and draw in the radius vector from the pivot point to the location where the force is being applied. If you wanted to use RF sine theta, you need to measure this diagonal distance, which could be tricky. You need to know the force. That's going to be pretty straightforward. That's just the weight of the car. And the trickiest part, though, would be you need to also know the angle between them. That angle would be very difficult to measure, other than just like taking a picture of the whole thing and measuring that angle with a protractor after you draw in the vectors. But in a physical scenario, this angle can be very difficult to measure. But instead, if we use r times f perpendicular, that's going to be kind of tricky because we'd have to split the force into parallel and perpendicular components based on this diagonal radius. And that might be difficult to do. But it turns out that in this context, the third one is actually the easiest to use, specifically because the force of the car is straight down. If you're dealing with a force that's purely horizontal or purely vertical, this formula usually becomes the easiest to use. Because if the force is straight down and we want the perpendicular component of the radius, what's perpendicular to straight down?
Horizontal.
Yeah, perpendicular to a vertical force is a horizontal direction. So if we want to split the radius into parallel and perpendicular components, parallel would be straight down, perpendicular would be straight to the right. So our perpendicular is just going to be this horizontal distance. So if you want to know the torque acting on the bridge because of the car, all you really need to know is the weight of the car and how far horizontally from the pivot point to the spot directly under the car.
Why is it R perpendicular instead of F perpendicular? Because isn't it perpendicular to F?
We're looking at the component of the radius perpendicular to the force. The idea is that the entire force, so the full weight of the car, multiplied by not the entire radius, but just the perpendicular component of the radius.
So then F perpendicular would be perpendicular to the force and not the radius?
If we were using F perpendicular, this second formula instead, then that's going to look like, let's say we've got this same radius, this same force. If we were splitting up the force into components instead, we'd be using a component perpendicular to the radius and a component parallel to the radius. So that would be F perpendicular, the component perpendicular to the radius itself, versus F parallel, the parallel component. And as usual, the parallel component doesn't matter. The perpendicular component is what makes the difference there. So you could calculate the torque by multiplying the entire radius times just the perpendicular component of the force. That's going to give you exactly the same result as the entire force times just the perpendicular component of the radius, because they would both end up being the same as R times F times sine of the angle between them. Angle between them being this angle. But in most cases of this sort, if you've got just a force pointing purely vertically or purely horizontally, it's usually much easier to split the radius into components than it is to split the force into components, just because of the different coordinate systems in use. So either way works, but if one of the components, if one of the vectors is already purely vertical or purely horizontal, it's usually going to be easier to split the other one into components based on that instead. Alternatively, if you're looking at several different forces acting on the same object that are all radially in the same direction, like let's say we had several forces acting along this same radius vector, it's usually easier to just use one unified coordinate system for the whole problem. So if all the forces are along the same radius vector or same radial direction, it would usually be easier to split up the forces into components perpendicular and parallel to the same radius, because then you'd just be using one coordinate system for the whole problem. On the other hand, if all the forces are perpendicular and parallel, or all the forces are horizontal and vertical, then it's probably easier to split the radius vectors into those components as well instead. So any of these formulas work, they all lead to the exact same result. You generally just want to choose the one that's going to be easiest to work with based on the directions of the existing vectors. You want to be able to set up one unified coordinate system that works for the whole problem. Any other questions on that? All right, then review those definitions. Also, if you go to math.andcheese.org, let me put the link here, math.andcheese.org/P7B, and there should be a link on there that says Kinematics Charts. If you click on Kinematics Charts, it just brings up a list of all the relevant definitions for all these important quantities: torque, rotational velocity, rotational acceleration, with their definitions, their units of measurement, how they're related to the other important quantities. Because this study of motion does introduce a whole bunch of new variables, and it can be difficult to keep track. So it can be very useful to have a reference card like that, just to be able to quickly look up all those important values. So review that, and we'll look into some more numerical examples next time. See you later.
Thank you.
You're welcome.